Let me start with, we're going to start with some of the basics. So people ask what I think are really good questions, and just to clear stuff up really. So one of the questions that we had, let me just try and find where we are. So yeah, let me start with you, Karanya. So pictures of the universe showed it shaped like a rugby ball, and is this how it is, or is this a modelling thing?
Okay, is this on?
Can you hear, Karanya? Yeah.
Okay. So the movie I showed at the very beginning, where we started from inside a galaxy and then zoomed into this rubber ball projection, it's actually a projection of the full sky. So we are inside a sphere, we are seeing the surface of the sphere, and it's just simply a geometric projection of that full set of information onto a map. Just like you can take just the surface of the Earth and project it into some other representation where it's either rectangular or elliptical in the same way. So it's a full sky.
Okay, thank you for clearing that. We're going to do all kinds of questions. Some will be quick, some won't be. One for you, Pedro, I think. Is there a reason as to why the speed of light is what it is? Or do we just need to accept that's what it is?
A value?
Yeah.
No, well, it's a value. It just has that value. I mean, there are some constants of nature. There are very few constants of nature, and they have a certain value. They just have that value.
So we just have to live with that.
Yeah.
Maybe fair to add, though, it's very, I'm sticking up for it being International Year of Light, you see. But I guess that a remarkable step forward in an understanding of light, as I mentioned very briefly at the beginning, was Maxwell's work. And I think the fact that that constant nature, you're absolutely right, is just a value, but the relationship it has with other constants of nature was a specific prediction of Maxwell.
Like relativity?
Indeed, yeah. So, you know, that for 19th century physics was a remarkable discovery, I think. That's my reading of it, that one could relate this sort of astronomical phenomenon to numbers that could be related to experiments in the lab.
So is it right to say that it's the cosmic speed limit, as it were, nothing can go faster than that, and that also happens to be the speed of light, rather than, it's not because it's the speed of light that that's the cosmic speed limit? Or am I just making it worse?
No, I think you're making it worse.
Okay. It's been said before, to be honest.
No, I mean, it's a good question, but I mean, I think the point that Martin is making is quite important, because the word unification has come up finally in the equation on the t-shirt, and in some sense Maxwell's work 150 years ago was one of, not the first, but what was a great step in unification. And one way of seeing it is exactly the way it's been said here. There's all these disparate numbers and they come together in this one way.
Yeah. One for you, maybe Marika. So somebody says, I heard that the expansion of the universe is measured to be, initial expansion, measured to be about 3.5 times the speed of light. How is this compatible with special relativity?
I mean, the expansion is at what point? I think you have to clarify the question. I don't know.
So this is the this is the expansion of space-time itself.
Yeah. So expansion of space-time does not have a speed limit. It's the information exchange through space that has a speed limit. So actually, the universe, the observable horizon can be said to be expanding faster than speed of light.
Okay.
It is a relativity.
Sorry?
Is the mic, are the mics on?
Okay. Maybe you have to talk out there. If you talk to me, you'll have to talk to the mic. Sorry. Is Hiranya's mic not on properly? Sorry.
I feel like I'm shouting.
Okay, we'll try and sort that out. In the meantime, I'm doing the quickfire questions now. Here's one for Martin. How will the LISA probes stay still to the extent that they could be moved by gravitational waves if they're in space?
They won't stay still, they'll be orbiting around the sun independently, and one of the key elements of technology that LISA Pathfinder will test will be our ability to control those orbits with attitude jets, just the way that other satellites are controlled, so that they can maintain, as best we can, a well understood orbit, which will be your kind of baseline against which you would then compare the laser paths to see whether there's been a change in that baseline orbit. But they're not in a fixed position, they're orbiting, and in fact the test masses inside, I was rushing at the end, but they're made of gold. that's the main reason for the budget being so high. That's to have as pure a quantity as possible, and they will be in free fall. They won't be attached to the spacecraft. They'll be sort of sitting there in free fall. So, sorry, I hope that elongate. I hope that's an adequate answer.
Okay.
Yeah.
And actually, somebody, I don't know who might want to state this up, somebody made the point that if gravitational waves, what's waving exactly? What is, what's the ripple in?
In the curvature of space-time, that's what's changing in time.
And then somebody else has said, what if you bend space-time, what does it bend in? Which I think is a great question.
It's a great question. I think it's relevant to, well, probably more than just our two talks, but certainly at least our two, a little bit of the one in Super Movie 2. For a long time, I wrestled with this question of if the universe is expanding, what's it expanding into? And lots of people ask me that, and I suppose in the end we just have to a little bit retreat to the maths and see what the others think, which is that actually we can talk about the intrinsic curvature of space and time without there necessarily being an extrinsic space into which it's expanding.
Okay.
Can I just add to that?
Yeah.
So, 2 points to that. So, I told you that Einstein had to learn this weird math. The whole point of that math is to do this, is to be able to understand the bending of space without having to think about it bending into anything else. But it's a bit this question of what the universe is, what is the universe expanding into, or what's before the Big Bang. What my colleague Jocelyn Bell has this really good answer, which is when people say, what was before the Big Bang? She will say, well, what's north of the North Pole? Right? It's that kind of question. It's the kind of thing that we've had to grapple with for decades, but the interesting thing is over the last decade, this idea that actually we might live in a universe with more dimensions means that actually the universe might be expanding into something. It might be evolving. So we don't even have to be completely honest in our answers anymore. We can just say we don't know.
So I'm going to move on to somebody else's question, which is that are these theories of multiple dimensions and infinite numbers of universes just plain wrong? Maybe that's Eugene.
I think wrong is probably the wrong answer. I think we have to be careful about when we say there's a multiverse. We have to ask ourselves, well, why do we even start thinking of a multiverse? And why should we do we make it up because it's cool and like science fiction? I think the important thing that we have to say is that a multiverse is actually a prediction of what the current state of our theories are.
I would like to say that some string theorists say that it's a prediction of string theory, and a large number of string theorists are quiet and let them say it, where perhaps they shouldn't.
Oh, okay.
I don't think string theory is at a state that we can actually say that's a prediction.
But this is not a string theory statement, though. It's an inflation statement.
But it still relies on quantum gravity, right? It still relies on basic ideas in quantum gravity.
No, I think it relies on, we can get
That's right, quantum tunneling, which presumes that you have some understanding of quantum gravity. People are doing crude, approximations of quantum tunneling. So, I don't think you can say that this is a sharp prediction at this point.
Oh,
Walk through the sort of string theory groups around the world. The west coast of the US loves this idea. The east coast does not, right? There are some very dominant people who are quite against this, and very distinguished people who are against this. And there are people like myself who are sort of in between and say, look, if we do this with the best we can do right now, we seem to see a multiverse. We've still got a lot to learn about the way we do
I think I agree with that.
So
this is why my answer has the caveat, which is in the state of current understanding of the theories. I think that is why we can. Maybe the people on the East Coast, okay. I'm from Chicago. Well, I need my theory. So I'm actually trying to do it, right? So I do both. I write papers and I can write papers.
And actually, Michael's question originally was not the multiverse, actually, it was extra dimensions, which isn't super
Yeah, I did mention both. But yeah. So are we believing in extra dimensions?
What does that mean?
What
I
is
knew
it
you
now?
would say that.
No,
So I'm not allowed to use the word believe. these people. I get told off for asking them what they believe in. Do you think that extra dimensions are a valid thing to explore?
Yes. Yes. There's no, I mean,
you don't think it's possibly a kind of excuse for just carrying on and sort of disappearing further down the wormhole, or rabbit hole rather? Or wormhole?
No, I think it's a perfectly legitimate concept to look at. And it may be important, it may solve a lot of problems. It may be that we will come up with very clear predictions that we can test. But there's no reason not to consider extra dimensions.
Can I add a little of that too? I think we also should look at extra dimensions. It's because it might be the way that we understand why we have dimensions, or we have four dimensions. I mean, if you want to understand why we have four dimensions, is it a number that is given to us, we have no choice, or is it maybe to understand extra dimensional theory, maybe there's a way to try to derive that we get four dimensions, or four dimensions we see now today. So I think and even if you don't believe in extra dimensions, I think exploring the extra dimensions might answer the question why we have four dimensions today.
Okay.
I mean, in the late 90s, when the idea of large extra dimensions became popular, I mean, to me it was extremely surprising that you couldn't rule this out already. I think for many people this was extremely surprising. So, I mean, as a theorist, I didn't find, I mean, string theory in its simplest models likes to have extra dimensions. I don't think it's necessary for string theory, but the models we understand best have extra dimensions, but they're not usually large. So, the idea that they were large was sort of an idea that people introduced for other reasons. And it was sort of astonishing that you couldn't rule it out. So I think, people learn quite a bit out by ruling it out, right? I mean, so now we would say that the simplest idea that there's one large extra dimension is pretty much ruled out, right? The simplest realizations, but maybe we learned a lot to do it. So,
Let me ask you a sort of question from Michelle. You've been very quiet. I couldn't begin. So when we're doing computer simulations, like you're doing with the Eagle thing, how do we know that actually we're not just getting a generic universe out? That it's sort of, there's a problem with garbage in, garbage out, isn't there? Where you've got to put the right numbers in, and presumably there's a whole field of numbers where you can get something that looks vaguely acceptable as dark matter.
Yeah, there are, and this helps us to constrain what can't be considered to be, for example, dark matter. So when we do our simulations, we tend not to do just one simulation. So we might do one big simulation, but we have a whole suite of smaller simulations where we play with all of the knobs that go into our simulations and look at the resulting universes that come out and try and see how similar they are to the real universe. And that's what tells us if we're getting garbage out, if we're putting garbage in, because we're getting garbage out that looks nothing like the real universe. There are different variations where we might be able to change one parameter a lot and still be able to match the real universe, but we need more detailed observations to try and understand that a little bit more, and we need to try and develop the fundamental theories that are going into the simulation to really try and not be producing, say, 12 of the same universe. But the thing is that when we do look at our simulation and we look at the real universe, we tend to choose the simulations that look most like the real universe, because they're where we're going to learn something about the things we can't see. So, for example, one of the things that we can't see is when we look out into space, we see basically snapshots in time. So, at a different redshift, at different points back in time, we can see galaxies. But we can't see how a galaxy from say 4 billion years ago becomes a galaxy today. But we can see that in the simulation, because the simulation involves each galaxy. So that that's one of the strengths of the simulation. But until we have simulations that look like the real universe, which we fortunately now do in the last 18 months, there's been some really nice progress on that. Until we get to that stage, we can't really say that much about what we're observing. But we can be critical of our models when we don't actually.
Okay. Let's get on to inflation, which a lot of people ask questions about, quite rightly too. So we put this straight to you, Haranya. So what caused inflation to start?
That's a very good question. Can you hear me now? Yeah. Okay, I think it's come back on, I can tell. Can I digress a little bit? So inflation is a way to fix the initial conditions features of the standard Big Bang model which appear very, very fine-tuned in the absence of inflation. So one then has to ask oneself if, does inflation itself need very fine-tuned initial conditions itself in order to start? And I would say at the moment that's an unanswered question. So once you get inflation going, it makes very strong predictions that you can go out and verify by observing, for example, the cosmic microwave background, and those predictions have been satisfied. And I think that at the moment we have to now ask questions about the physical underpinning of inflation, and one of those questions is it very unlikely that inflation will start? Because once it starts, then you can keep it going. Long-term inflation, I think Eugene just alluded to that, in the context of the multiverse. So it's a good question, we don't know the answer yet.
All right, so what made it stop?
What made it stop? It has to stop by design, okay? So if inflation, let me just clarify that statement. It has to stop locally in some parts of the universe in order to get a universe like ours. Our universe is expanding in an accelerated state right now, and that can be thought of as a kind of inflation, but it's not, because the energies are too low. But in the very, very early universe, the universe also expanded at an accelerated state if inflation happened, right? But to get a universe that's dominated by radiation and matter, which we need in order to build up galaxies and people, we need inflation to stop locally. So that's, in fact, a design feature that you have to put into your model. If your model has inflation going on forever throughout space, it's not a good model. And the way that you get it to stop is a little bit technical. I think we don't want to quite get into it. But it is a feature of models that inflation has to end. Yeah.
Okay. So, let me ask you, Marika, as a theorist, do you find inflation a compelling idea, or do you find it? Yeah. Because it comes in for a lot of criticism in terms of it hasn't got any physical basis in it. It fills a few gaps, but
that's right. The problem is that your best models of quantum gravity, it's very hard to get to spit out inflation. It's very hard to spit out, the simple inflation of potential. It's very hard to get it to stop, as Anya said, to build that in. We're not at we're not in a status of, say, what in the photon field. So of course there are many, many models. Anya tests many, many models, many different potentials. But the thing that's unsatisfactory is that it's not coming out of our fundamental theory. But still, as an idea, it's clearly compelling. It's still, it clearly fits the data, solves many problems.
Yeah, to that. It's in fact, I think, a test bed for fundamental theories. So if you've got fundamental theory and if it's very, very hard to get something like accelerated expansion out of it, it might be telling you something quite deep about fundamental theory. And in particular, if you measure this signature primordial gravitational waves, it has implications for theories of physics that operate at the Planck energy, which is the highest energy you can ever go to, where crazy things happen, like Eugene said. And you really do, and it's high. That signature, and it's high, it has direct implications for a theory of quantum gravity.
And so Michelle and Eugene, when you're training in physics now and training in cosmology, is this just accepted that you accept it, the Big Bang plus inflation and everything else? Well, it's taught. Is it taught as
it is
the way?
If you like, you're going to graduate because you're doing the PhD or even a master's class. I think this is, in a sense, standard law. And I think there's always standard law depending on reflection. There will be a set of caveats, right? Maybe some people will be stronger, maybe a little less, but it is, if you like, standard. And even if you don't believe it, you have to know it, or else you won't be able to do it.
And at the same time, when you're doing these courses, when you're going through your physics training, you tend to be encouraged to question everything. So it doesn't. It's not that yes, it's taught to you, but you still understand. You still try and understand some of the flaws in any of the theories and any of the things that we talk about, and you try and understand how to question them and at what points your model becomes completely dependent on them, in which case you really need to understand how that could break down.
Michael, can I just add something?
Yeah.
In the last few years, there's been an attempt to redesign the school curriculum in Scotland. It's called the Curriculum for Excellence. I always think it's a rather silly name. What are they going to call it? Curriculum for Mediocrity. operations, frankly, more than a curriculum. But I've got involved a little bit in helping to reshape the physics, essentially the equivalent of the E level and the one before that called the higher. And we've got some stuff about inflation and dark matter and dark energy, but I heartily endorse what Michelle just said. The object isn't to present to, as this is the same as Newton's three laws, but just to give them a framework in which they can ask the right sort of questions, because we were painfully aware that teaching physics was becoming, well, this is a bunch of stuff done by dead guys 300 years ago, and we just wanted to shake things up a bit.
Yeah, and that's great.
It seems to be going down well, but the teachers are a bit scared.
Petra, let me ask you something on a related thing. Several people ask questions about modified theories of gravity. So this idea that you have sort of modified Newtonian dynamics model, and alternative. And people say, why are we not giving more effort to seeing whether they're a better fit than having dark matter kind of scattered through the universe?
Well, okay, so the first statement is we take GR and we extrapolate it. So we extrapolate it to very early times or to very large scale. And this is a huge extrapolation. So for example, if we were talking about late times, we tested general relativity incredibly precisely around on the Earth, but most importantly in the solar system, on scales of about an astronomical unit. And then we extrapolate 15 orders of magnitude and apply it to cosmology. And you can ask yourself, are we allowed to do that? And the answer is, well, it works pretty well. The plots that Kiran was showing is assuming GR and some really basic assumptions, and you fit the universe. You fit the universe incredibly well. It leads to these odd predictions, which is dark matter and dark energy. So it's perfectly legitimate to question the possibility, to say, okay, maybe we've got gravity wrong. If we can't independently test general relativity on cosmological scales, maybe we should look at other solutions, other possibilities. Well, I think we can in principle test general relativity on cosmological scales, but I do think we should look at other alternatives. There's a really fundamental problem, which is, I think, Eugene, you mentioned effective field theory. If you apply your best knowledge about how the laws of physics behave and how you extrapolate to different length scales, it's very difficult to come up with a way of allowing new modifications to gravity on very large scales. Very large scales means very, very low energy. It's very difficult to do. I mean, it's possible, but it's not very easy. And that's one of the reasons that a lot of theorists shy away from doing this. They just think it's something that doesn't make any sense. The fact is, it is a huge extrapolation, so you really have to look at these things in a different way. You brought up probably the worst example, the modified Newtonian dynamics, and it's a really grotty field, okay? And it's one of those fields where I looked at it about 10 years ago. I wrote a paper in that field, which was a calculation. And interesting things happen. The first of all is you are tainted for life. That's the first thing. The second thing is you realize that the tenor of the discussion is completely mediocre, in that people who write papers on modified models, this thing, often will only focus on one specific aspect and ignore everything else. On the other hand, people who don't believe in modern and won't believe in dark matter will tackle one very specific thing and will look at everything else. So the tenor of the discussion between both sides is pretty bad. People are quite passionate in a very subjective way. So I steer clear of that field completely. Personally, I think that the evidence for something clustering out there is stronger than for Mond. Having said that, there are a couple of things that come out of Mond which are remarkable. People haven't been able to explain. They're phenomenological statements about data. They're not theoretical statements. My personal view is it's very difficult to consider modifications of gravity. I think the first thing to do is to actually see if there's any independent way of testing gravity in different regimes, trying to satisfy it.
Can I add? Yeah. So, first an aside, which is that if you say more, you do a paper and more, you think it's a lot. My first PhD project was more. And thankfully I didn't write a paper on it, that's what I said. But let me add a little bit more about what Trevor was saying about how hard is it to write a theory and why GR is so powerful, that's so good. There's a theorem that you never heard about, and which is super great for me, is that if Einstein never discovered GR, so we can ask the question, who would discover GR? And I can give you the answer, it was Stephen Weinberg. And because in 1964, he came up with this theorem, which says, if I just believe in the stuff that I talked to you about, this particle flying around, and then you say, well, if I believe all this physics, and I just believe that, I don't care about the quantum calculation, what theory can I write down that would behave like gravity? It turns out that that's a unique theory you can write down, and that's GR. And that's and in a sense, they're saying that GR is somewhat special, but it's also very useful theorem because it tells you that what you need to break GR. So for example, the theorem will require that you have to believe in special relativity. You have to believe that the Coulomb's principle says you obey. In other words, gravity given you by gravitons and nothing crazier. So if you those are the ingredients you put in, and out come one unique theory, which is GR. So in the field where
higher assumptions, then you squeeze out the scope for the unexpected.
Yeah. I mean, one of the difficulties playing devil's advocate, I would say, is that when we suspected the existence of dark matter since the 1930s, and been looking for it quite hard since the 1970s, and people have said, Vera Rubin said in 1970 we'll find it within a decade. Martin Rees said exactly the same thing in 1980, and here we are in 2015, and we haven't seen it. And so, you could say, well, how long do we keep believing you when you say we are going to find it, and then everything will drop into place.
I mean, I think that's an important point about scientific honesty. That, scientists will have to be honest. So as Martin showed in his gravitational wave, estimates, to really put pessimistic estimates and explain why you put them is really important. But unfortunately, politically, it's very difficult to do so. Politically, we're not really encouraged to do so. I'm not an experimentalist. I'm not writing cases. But I see that people put very optimistic. So, for example, for the kind of black hole physics I mentioned, where you see deviations from Einstein's picture of the event horizon, which are big enough to be resolved by the event horizon telescope or gravitational waves, it's very unlikely that the current generation of experiments would do that. I was strongly encouraged to sort of join in and actually make a prediction that they might see it. And I was really reluctant to do so. I mean, I didn't do so because I think, the corrections are way too small. But in a sense, if you kind of make a scientific case that says you might find this, it can often be helpful to you. So it's a difficult balance. Now with dark matter, I think we are close to the point where we have to find it. And certainly also gravitational waves. We have so much indirect evidence for gravitational waves, like the Hawes-Taylor. So that's something you must find at some point. If your machines are working properly. I mean, dark matter. Yes, a lot of the estimates over the last years have been more optimistic. But it's difficult. I mean, maybe they should be more honest about the more pessimistic scenario. But it's difficult when you're asking to fund them to build something.
Yes. I mean, but was this true of the gravitational waves, and that people thought LIGO would find gravitational waves?
I play the plausible deniability card because I wasn't involved in the field at the time.
It wasn't his fault.
I've talked to some of them, because what you were saying, Marika, about, actually it was you, Michael, about the various decades where dark matter discoveries were predicted. Well, there were people saying things like that about direct detections of gravitational waves just before my time. But it's very interesting to talk to them about the sociology of that. In fact, there's a sociology professor at Cardiff and Harry Collins who's written several books on this, and they're fascinating reading. So I think there's a lot of, I don't know enough about the sociology of this to really comment as an expert, but certainly as a bystander and now as a participant, I find big questions and tensions between how much to promise when you get funded, and how much to retain your scientific integrity.
We've got a question that's kind of related to this, I want to ask. It's about the movie Interstellar, and it says, a new theory describes black holes promises to change the nature of human civilization in the movie. Can we expect similar groundbreaking advances, or, from all this kind of research, I think, do we find a connection between, the probably spin-offs technologically? I mean, is all this kind of research esoteric, or do you think it's important that it's linked to sort of advancing civilization, as it were?
But there are spin-offs. So people often say, string theory is completely untestable, right? But actually, people who work in string theory often have on the side interests or things come out of it on the side, which are direct sort of connections with the experiment. So, for example, I myself at the moment am interested in quantum information, but the things you write there, I'm not really talking about building a fictional Dyson sphere around a black hole. I'm actually interested in can I set up an experiment in the lab where I can measure this quantum entanglement? What would the answer be? And that's actually something which genuinely, seriously, some people go and do in a lab. And the connection between string theorists and people doing quantum information, people doing cold atom, that kind of experiments, there is a really interesting dialogue. So there are spin-offs on it. No, now is it a spin-off of technology? For me as a theorist, no. Of course, for those building very sophisticated experiments, obviously there's a lot of technological technological advancements. But certainly, I mean, the interstellar, like, you know, we're a long way from going through a wormhole. So,
You say
yes.
that. Michelle, do you find that people say, well, you explain the research and people say, well, yeah, but okay, what am I going to get out of this?
Yeah, you do sometimes get that. And I think because the specific research that I do is quite computer-based, it involves, as I said, a lot of simulations, it makes it a little bit easier to kind of connect it back to the real world. So in my department, we work with Intel and other high-performance computing companies to encourage them to develop for us, the kind of front of the field kind of computers that we need to do our research. And we also worked with computer scientists. So while they're helping us to build codes that will evolve our virtual universes, the algorithms that they develop can then go back into other research or into other areas in which computer science is really key. So there are connections certainly within what I do with the computational world, the advantages of the technology being advanced.
Would that be true of the CMB?
Yeah, well, okay, so the CMB is not the example I would use. I also work on very large galaxy surveys. So you need these very specialized, very large format CCDs to measure galaxies and make huge maps of them.
Devices,
Yes.
so that what you have in your digital camera.
That's right, that's right. So there was a co-development with astronomy as well that's now gone into all these applications that you can find on the phone. But the next generation devices are these huge CCD cameras. I'm working on the dark energy survey, and there's an upcoming survey called the Large Synoptic Survey Telescope, which is even bigger format CCD. So those kinds of devices are developed, and that technology then comes into the more commercial applications. But in addition, the data rates for these surveys are getting so high that we're starting to work with companies like Google, for example, because we have these huge data sets. No human being is going to be able to go and look at these trillions of objects that are catalogued, and the LSST, Large Synoptic Survey Telescope, is going to make a movie of the sky over 10 years. It's a huge amount of data, and to find interesting information out of that, you've got to use these very sophisticated machine learning algorithms, which can then translate into what people use to search through databases in Google. And the square kilometer array has even more data coming in. You can't even store all of it.
That's another thing.
Yeah.
There are two really good examples of this. So, in the 1970s, people tried to figure out how to do collisions of black holes, black hole mergers. And there was a guy called Larry Smart who was one of his thinker of it. And he realized that you needed to set up a supercomputer. You needed to set up a supercomputer to do the simulations. And he set it up in Illinois. And there were a lot of technological offshoots, but one of the technological offshoots was what effectively was the first web browser. Okay, so all these, the Internet Explorer, all this stuff. First one that really people used was something called Mosaic. It was invented by this gang. Another notable example is there was an Australian astronomer who hears about Stephen Hawking stuff on Hawking radiation and goes to visit him, and he goes back to Australia and he wants to figure out how to measure it, and he has a team there, and one of the things that bugs him is the connectivity between their computers. So he comes up with wireless, and we all use wireless. And these are just two incredibly significant examples of offshoots from what we do.
Can I just add to it? I mean, a lot of the funding that, in my field is actually coming from the offshoots. So we have students who are funded by large data collaborations. We have students who are funded for next generational computational modeling, for the skills which would be transferable, across in many, many fields. And we have students who are actually funded in web science, and we have students who are funded by the electricity companies. Now, where's the connection there? You get surprised about that one. This is stability of electricity networks. So this is related to problems in topology, which in turn can be solved with string theory techniques. So they do this on the side.
sitting beside someone in the plane as they were flying over the detector, and his neighbour, who didn't know he worked there, said, "That's a government time machine, government-funded time machine." And he said, trying to just keep the conversation going, "Well, why is it L-shaped?" And she, a theory for that, the one arm was to send them back in time, and the other one. So I've used that a few times talking to Bible and then reassuring people that it is not a time machine. So anyway, I don't know what I was thinking about the real prospects, but like it certainly isn't one.
See, that's how it got its funding, though, presumably telling the government that lots of lies. I mean, wormholes are theoretically possible. Do we ever look for them? Is there a chance of finding any?
Well, wormholes are theoretically possible, but actually you need very, very strange energy, mathematically very strange behaviorist energy to actually create a wormhole. So there was a lot of interest in wormholes theoretically, I guess, 20, 25 years ago. But the idea that such strange matter could exist is considered very unlikely. So it's not something that people really go out and look for.
The very state.
Yes.
Even if you have this matter, then try more people. It's collapse. Yeah. You'll get through.
Breaking my heart. Do you think about it? I mean, do you sit there on a Sunday afternoon thinking, you know what I'd really like to work on?
No, I mean, I say it was something where some of the main ideas were fleshed out 20, 25 years ago, and I don't think people have anything to add to that.
Right.
You have to bring, it's like my going back to the drawing board. You have to actually have something new to put on the table to go back into.
What people are thinking about, I think, is what is time and why does it have one direction? And is that coupled to very, very special initial conditions in the early universe? Does it have a fundamental character or is it emergent? Those sort of questions are being very actively fleshed out.
But no time machine.
Maybe the time machine will come out of thinking more clearly about time.
I'm interested to kind of pursue this partly because Pedro mentioned the idea of sort of fads and fashions and things. Relativists were out of fashion for a long time.
Used a lot.
But and then are there things now that are very much in fashion, or things that are very much out of fashion which you'd like to see come back?
There are things that are in fashion. I mean, well, there are things that are spoken about. I think are quite cool. There are some people who work on it. This idea that actually fundamental physics isn't local. In other words, you can't describe it in terms of things happening here. You have to describe things in terms of processes. In other words, as the language that's used as scaffolding. Stuff goes in and stuff goes out, and whatever happens here, you can't just kind of diffuse thing, just this kind of diffuse thing. So that's very much in fashion at the moment. I don't know, extra dimensions is a little bit out of fashion, but I hope it comes back into fashion again.
Modified gravity is in fashion, isn't it?
I think that's a kind statement to make.
Not mod, I mean.
No, but even modified gravity, there are a few people that talk about it, but then it's more in fashion than it was, but that's not saying a lot.
It's maybe also worth noting that we can ask this question within the context solely of relativity and cosmology, but if you look at the field of astronomy as a whole, when I began at university about 35 years ago, there was this professor there who passed away a few years ago, Archie Roy, whose career had been in celestial mechanics, which even then, we felt was rather dry and outdated. But that sort of got a renaissance with studies of stability and chaos, and then it's got an additional renaissance with the discovery of extrasolar planet systems. So, I think, it's very gratifying to see all the people come here today. Cosmology has had this enduring fascination, but we should never lose sight of just how fascinating the solar system and the questions about life on other planets are for the wider public as well, and indeed for funding agencies, because there's been significant funding put into those.
So, as a theoretical physicist, one of my colleagues describes, theoretical physics by a hamster wheel, things on the hamster wheel. And the thing that's at the top and you think you never need to know as a student, that's the thing you should learn, because that's the thing you will need 10 years later. So I very much agree that things come into fashion, things come out of fashion, but it's not just whimsical like fashion clothes. Right? It is really driven by conceptual progress, by a new idea going on the table, by new data, by progress. So it's you know, if people are not working on one, if the community in one is not large, it's because the judgment of many of the community is that that's not where the interesting things lie. You know, if many people work on inflation as opposed to other models of the early universe, it's because most people think that's the most, you know, most appealing, that's the most satisfying thing to do. In a sense, the community as a whole kind of judges what's the most promising.
Yeah. I've got a question that maybe Eugene could answer. What would be your advice for people who want to become physicists?
Get an engineering degree.
You're both engineers, yeah.
Wow. I think okay, when somebody comes in and say he wants or she wants to do a PhD with me, I think the question that I throw back at them is that do you really want to be a physicist? And then not just theoretical physicists, but I think first I would ask them, are you because to be completely blunt, I mean I think the idea of physicists is really, really cool, but to actually get there is actually not cool at all. It's actually a lot of pain. And then if that person say, okay, I want to be a theoretical physicist, and I think advice, I mean, I guess I can give what my advisor gave me is that I think he didn't give me a lecture. I think what I got from him being a student is to always have a healthy disrespect for authority. You got to be loud and not maybe loud, but you got to challenge everything. Right, to build, which exhausting thing to build, to challenge everything. You read a paper, it's easy to absorb, but you try to find things that strong, is it wrong? Where the assumption is the question I always ask, where the assumption, what is the fundamental thing that makes this work? I think those are things that this is the kind of the habit that I would say that theoretical physicists should have. Just have a healthy skepticism, even sacred cows. So I think that's what my advice.
Michelle, you got anything to add to that? Somebody wants to follow in your footsteps. What should they do?
Well, I think first off, coming to an event like this is probably a pretty good start. But what Eugene said about really being sure before you start that this is what you want to do, it is a really, really grueling process to get through a PhD. It shouldn't be taken lightheartedly, and you need to make sure that it's not just the ideas of physics, but actually the workings, like what happens on a day-to-day basis in my life anyway, is that I sit at a computer and I write code. That is the main thing. In other people's cases, maybe they're working out equations, they're trying to solve equations. So you're not always thinking about the big picture. Sometimes you're really trying to work out details, and you've got to be sure that that level of physics.
Okay, I think we've got time for 2 more questions I've got here, which I'm going to ask each of you to answer. And the first of those questions is, how do you think the universe will end? So based on what we currently know about the evolution of the universe, what would you say is the most
assumption is that it will die. Something will happen that the wrong time will die. It will die by new process.
Okay. I don't even need to answer that. I'm just feeling the vibe in the room.
There's a credit paper by Martin Rees, 1968, which is the mythology of the universe. It's exactly like that. And quantum radiation hasn't been discovered yet. So new sources will all end up in the little black hole as well. You get rid of that one.
Not even little black hole.
Black holes is the black hole. I think there was a new scientist article that somebody did ago that looked ahead to the time when we were so positive to see that it was a heading an awful lot of viewers.
Yeah,
Great.
Yeah, it's quite depressing after that. Okay, one more question which I will ask each of you, but you don't have to do it all. If you could ask one question of Einstein, what would it be? Who's going to go first? Okay.
I don't know what the question was, but the interesting thing about Einstein is that last month, in November 2015, he finally began to realize how he was still up his theory. What's interesting, and it's an interesting big thing about science at the time of this, he would do something and he would write a paper, and every week he put out a paper. And he got it, he thought he had it right in around 2012, 30 he got it right. He tried to figure it out, and then he went and documented the paper. And you can see that he puts on the paper. And this is right at the beginning of October. And he puts down another paper, and he's going back. Then he puts down another paper, and he jumps back all the way back. And then he puts down the right paper. Now I'd like to know what made him jump back.
Anything else?
I think that was a motivational question, something trying to get some inspiration, but what I find sometimes in my work is, you're working away, and you get this kind of block, and you can't seem to go anywhere. Everything you try, everything seems to go backwards. And I'd be interested in knowing what it was he did, especially because he did a lot of his work on his own. We're definitely working collaboration, we do have other people to encourage it along. What was his driving force? What was it that made him go back into his desk and work it out? It just kind of kept him going. It was just a real difficult he felt because there was something really more there that he was, some goal that he could see that that's the end point.
Actually, that really well documented. Einstein biographies and so on, I would tend to read more of them. But while I have read quite a lot about the development of quantum physics, apart from just the appreciate stuff, go to something else and all that. So I think I'd like to get the chance to talk to him about what he really knew of all of that at the time, and what he would use for things like, the strong evidence we now have in favour of quantum handling, how that would fit into Einstein, what his view if he still was saying what the Einstein really like to do.
What do you eat in a real bar and get
It's a very particular kind of brain spirit, isn't it? There's actually when you look at that's what Einstein's diagram showed in his cat out by Paul Halpern. And it's about that kind of latter-day search that Einstein made and looking into. He's constantly just trying to find a way to unify quantum mechanics and relativity. And it's quite it's not depressing really actually, but you sort of realise that he's on this quest that he's never going to fulfill. It's extraordinary kind of thing to do.
I was imagine that one last time when he died when he was quite young, he was killed and it was the time lived long enough to be allegedly making some quite ridiculous and regrettable statements in his physics towards the end of the 19th century. And I guess I'd like to know more about that latter phase of Einstein's life and how he frustrated. He's become frustrated by that. I think that was
Okay. Yeah, so another book. And we're going to have to wrap it up there. Can I ask you to join me in thanking our panel for their contributions all day?
Just to wrap up, I have a couple of announcements to make. First of all, where's Ian? Is Ian here? Ian, your hand up? He hasn't gone home because I've got his voice for cards. Ian, if you're here, come and see me and get your Oyster card.
and on this venue, it helps make these events better. If you've enjoyed today, you might be interested in our other instant excerpts that we have coming up. On the 12th of September, Anna Smith will be talking about consciousness with some other speakers that we are currently lining up. And for those of you who missed Quantum World in February with Jim Al-Khalili, the response we had was so fantastic to that event that we're repeating it on the 14th of November. So that's the 14th of November for the instant excerpt on Quantum World. If you came to Quantum World in February, this is the same one, so come again unless you loved it so much you want to hear our speakers again. We have your email, so we'll be sending you an email in the next week or so with details on how to buy those tickets. And you can also keep up to date with our Eventbrite page and book tickets to these events through that. My mind is absolutely buzzing with civics, with ideas, and with possibilities. I hope you've enjoyed today as much as I have. And before we thank our speakers again, I'd like to say special thanks to our host, Michael Brooks. During the break. The amount of questions that we've had from you has been absolutely phenomenal. So I think the speakers and I would also like to thank you. Thank you so much for today. Thank you.
Okay. Okay. Yeah. That's fine as well. Very quick question. That's fine as well. Oh, thank you.